Yes.
Okay. Okay, hello everybody. I hope everybody is doing well during this time of crisis. Okay, so when we do fMRI experiments with gradient echo acquisition, what we usually observe is an increase of the fMRI signal on the y-axis across cortical depth, white matter on the left, CSF on the right. That's from a study, from our study, but you can find it in a lot of other studies, this observation. However, if you look at electrophysiology, what we see is when CSF is plotted on top, white matter on the bottom, that we have actually a very inhomogeneous depth profile. So how does this kind of depth profile be translated to yield something like fMRI signal profile, what we are seeing here? One side remark, when we plot fMRI signal, white matter is often on the left and CSF is on the right in the x-axis, or the other way around. In electrophysiology, CSF is on top and white matter is on the bottom. So just keep this in mind, and there are good arguments for all of these choices. Now, how do we understand this? We have developed a model to describe the transformation from neuroactivity to fMRI signal. This is plotted here. So CSF again on top, white matter on the bottom. And we say neuroactivity consists of excitatory neurons and inhibitory neurons. They are connected to the blood vessels via neurovascular coupling. And then they change blood flow, and which then changes in the venules and veins, deoxyhemoglobin and blood volume. And if this would be the whole story, then the spatial profile of the fMRI signal, which is sensitive to deoxyhemoglobin, would be very similar to the spatial profile to neuroactivity. However, if we look in the tissue, the deoxyhemoglobin in one layer, one depth, has to go somewhere outside of the tissue to the ascending vein. And the way it does is going to the ascending vein, and then is transported unidirectionally to the ascending vein, which then is transported out of the tissue and ultimately out of the brain. So if you now look into this, what we see when we look at one cortical depth, we have deoxyhemoglobin changes and oxyhemoglobin changes, which goes to the ascending vein, which is then transported to the upper layer, which means this change here has a local component from the same depth and a non-local component, which is coming from the bottom layers, which then means we have a unidirectional spatial blurring when we do gradient echo bolt signal imaging. We have also other effects. For example, our voxels are much larger than the individual cortical depths. So we have a voxel point spread function. We have also recently more and more discussed, we have also orientation dependence of the cortical tissue relative to the main magnetic field. After all this transformation, what we have is a bolt signal as a function of cortical depth and time, which looks like this. So it looks like very complicated. So the main message from this is for laminar and gradient echo bolt signal, it is spatial and temporal indirect reflection of neuroactivity. However, if we are able to sort of describe mathematically the chain of events from neuroactivity to laminar bolt signal, we can use this framework to optimize and characterize our acquisition and analysis choices. For example, what's the point spread function for a given voxel resolution? How many layers should we actually calculate when we invert the bolt signal? Should we use 3 layers, neural layers, or 6 layers, or 10, or 20? So we can use this framework to do theoretical investigations on what's the best approach when you use gradient echo and what are the drawbacks and the possible artifacts and confounds. In the next slides, I will describe one approach how to remove ascending vein effect. This is described in our recent paper. And also David Norris Group and Heinzle and Klaas and Stefan have proposed models quite similar to what we have proposed. So here you see the bolt signal as a function of cortical depth. Again, white matter is on the left and CSF is on the right. And the induced changes in one cortical depth. So for example, if you take the light blue curve, we have changed blood flow in layer 6. not surprisingly, we get bold activation in layer 6. However, because of the draining of deoxyhemoglobin, we also get bold activation in layer 5, layer 4, layer 3, layer 2, and 1. If we go to next layer, if we induce layer activation in 5, then we get activation in layer 4, 3, 2, and 1. However, because blood flows in one direction in the cortical tissue, we don't get any activation in layer 6. This was described in the paper of Marquardt et al. Now, how do we apply this knowledge? So we took our fMRI signal as a function of cortical depth again. The different colors are just different conditions. And we call this method spatial deconvolution, even though it's not a deconvolution operator, but we probably made a mistake calling it that. It's sequential subtraction. And the idea is the measured signal in layer 6 represents the local activity in layer 6. The measured signal in layer 5 is, however, affected by some leakage from layer 6 with a certain weight. And this weight we take just from the calculated theoretical estimates how much layer 6 affects layer 5. Then when we subtract this contribution, then what we are getting is the true layer 5 activity. And then we go to layer 4 and so on. If we do this, so if you see, we see this normal increase from white matter to CSF. However, if we do this, what we are seeing is a bump in approximately the middle layers. We used a very simple stimulus. It was just light intensity changes, which is a strong feed-forward stimulus. And we expect actually in the middle layers higher activity on the neural level. We don't see this here, but after this deconvolution or sequential subtraction, we see this increase in activity in the middle layers. So that's obviously not a proof, but it is encouraging because it shows it's plausible that actually this was not plausible, but this would agree quite well with electrophysiology. To summarize my talk, in the gradient echo bolt signal, laminar fMRI signal is ascending vein weighted. This leads to unidirectional spatial blurring towards the surface of the cortex. And as a consequence, laminar gradient echo bolt signal differences between conditions may be misleading. However, I want to make clear, I'm not saying that laminar gradient echo bolt signal differences are wrong. What I'm saying is examine your data very carefully, whether some other effects in addition to neuroactivity differences might play a role. Our model, based on mass balance principles, can account for this effect during steady state, and I have not shown, but also during transients, because it's a dynamic model. If correctly accounted, then the advantages of the gradient echo bolt approach, what Cheryl was talking about, like large brain coverage, ISNR, can be exploited without the disadvantage of the ascending vein. Of course, this is a model, and all models can be useful or useless depending on what they do, and we have to validate it. The validation of the model can be done with animal or human electrophysiology, which actually we are pursuing, or with other measures where we think they might be less affected by this kind of artifacts like VASO. And actually Renzo has tested some of the analysis choice for gradient echo bolt in his blog in layerfMRI.com. And we have used artificial labeling blood flow, a submillimeter, which is we are about to submit. And also there we found, like in Renzo, that actually the model, the spatial deconvolution, gives very plausible results comparable to VASO profiles and blood flow profiles obtained with ASL, which is very encouraging. And we have to sort of continue testing the model in order to see what are the limitations and what is its usefulness. And that's it. Thank you for your attention.